How we doing?
Good.
Good?
Basically Friday.
Basically Friday, it is. It's true. What questions do you have? For here? Don't know. Not today. Your next major assignment, I'm going to assign that next. The next major assignment I'm going to assign next week. Your next exam will be later in the semester.
Dangerous question.
What's that? About when the next exam is?
All being prepared.
It's tomorrow. You didn't know that?
It's tomorrow on Good Friday.
On Good Friday.
Why do we call it Good Friday?
All right. Let's. I'm going to go over the file that I sent on Tuesday as well, just to talk about where that error was that we had in our spreadsheet. It was a small error because it looked like a small error because it was a small set of data. If your data set was bigger, it was going to be compounded as you went along. But before we do that, let's just kind of review what it means to be a spline. Make sure we all are on the same page with what it means to be a spline, and in particular, a natural cubic spline. So this is actually number 9 in your text. It's on page 278. They give you a piecewise defined function. The first piece is 28 plus 25x plus 9x squared plus x cubed. That piece is defined from -3 to -1. The next piece is 26 plus 9, that's a 25x there. 19x plus 3x squared minus x cubed. And that piece is defined between -1 and 0. Next piece is 26 plus 19x plus 3x squared minus 2x cubed. That goes from 0 to 3. And the last piece, -163 plus 208x minus 60x squared plus 5x cubed. And that goes from 3 to 4. And so what they ask you to do in this particular problem is to show that this piecewise defined function is a natural cubic spline. Rather large list of numbers there, list of pieces in the function. Notice when we've been creating our splines so far, we've been writing it in terms of the powers of the endpoints that we're interested that we are matching up. But this one, they just multiplied it all out, made it look nice. But the idea behind this particular problem is just making sure that we understand what we mean by what a natural cubic spline is. So we had those conditions that we need to worry about in order for something to be a spline, generally speaking. What were the conditions that we need to make sure happen if we're making sure something is a spline? What conditions do we check? Yeah, so at the left and right endpoints, at those interior points that are subintervals, we make sure that those things we have the pieces matching, correct? So when we had a linear spline, we just made sure that the sticks were coming to the same point, right? What did we make sure worked for quadratic splines? What did we make sure matched up at the interior points? Yeah, the first derivatives also match as well as the endpoints, right? And then for cubic splines, we would need to check second derivative as well, right? So that's all this particular problem is asking you, is making sure that all those interior conditions are met. Remember, again, we call all the points that we have knots. When we're talking about splines, we refer to them as knots. So we want to make sure that those conditions on the interior knots are met, right? So for all of your interior knots, which in this case we've got 3 of them, we got -1, 0, and 3, right? So we need to make sure that the limit as x approaches -1 from the left of your function is the same as from the right, making sure those endpoints match. But you also said that the first derivatives and the second derivatives also had to match, right? So making sure that the limit from the left of the derivative, assuming that it's going to be defined, is the same as from the right. As soon as I'm using that notation, I'm assuming the derivative makes sense here, but we can do the limits just by taking the derivatives of polynomials. And then likewise, making sure it also works for the second derivative. I'm abusing the notation a little bit. I'm assuming the derivative already exists when I'm putting it in. Basically, this would be when I'm putting it in this way. Pardon me. When I'm putting it in this way, I'm assuming the derivative already exists, even though I would need to check this condition to make sure that the derivative actually did exist. But anyway, I need to check it for -1. Where else do we need to check these conditions? 0 and 3, right? I need to check it for the other 2 conditions as well, right? So I'm not going to write it all. I'm not going to write out the notation for each of those, but I would also need to do this. I need to check these conditions at 0 and at 3. All right, I got to check them at the interior knots. Okay.
Just the endpoints of these middle 2 equations.
Say that again.
Just the endpoints of these middle 2.
Yeah, so it's this endpoint here, this one here, this one here. We need to make sure those pieces match. Yeah. The fact that it's a natural cubic spline tells us one extra thing that we need to check. It's telling us something that happens at those last 2 knots, the ones that are at the ends. What does the natural cubic spline part tell us? What do we need to have happen for a natural cubic spline?
Second derivative 0.
At those endpoints, right? The second derivative is 0 at -3 and at 4, right? Remember we did the natural cubic spline, or sometimes it's called, I think they call it, they may not call it, I'm just trying to remember what I read. Natural cubic spline means the curvature is 0. I think they also call it curvature adjusted spline. But anyway, we also, at x equal to -3 and x equal to 4, we need, technically, I can't do the derivative at an endpoint, so I really need to talk about it as a limit. I need the limit as x approaches -3 from the right of the second derivative to be 0, and the limit as we approach 4 from the left to be 0 as well. We make the curvature 0.
Why does it say 0?
Remember, when we created all of our equations to create cubic splines, with those interior conditions aren't enough to give us enough information to find all of the coefficients as a unique solution. So we needed to add 2 extra conditions. This is just one way to do it. There are other ways to do it, but this is what we choose to do for a natural cubic spline, make the curvature 0 at those points. It's actually just a choice that we're making. There are other ways to do it as well. We'll talk about one of those today.
How do you choose it, but the derivative equals 0? Function just doesn't, or it doesn't have a second derivative 0 at that point, then I just like screw.
No, well, we are given points, and we're trying to find. This is just saying check to see that it really is a cubic spline. If it's not, then you are screwed. This isn't a cubic spline.
Okay.
If this one doesn't satisfy, then it's not.
Right. Just make the 0 constant.
No. Well, that's what we do when we're trying to find it ourselves. Right now, they're giving us the function, and we're checking to make sure that it really does. Because if it doesn't, then it's not. Yeah, you're exactly right. I can't make that particular function do something that it's not already doing. But when we're trying to solve one for ourselves from the set of data points, then we can force it that way. All right, so lots of things to check, but all of them are pretty easy calculus ideas, right? Because I just need to differentiate polynomials, right? So if we look at first derivative here, we've got 4 polynomials for the first derivative that we need to take. So the first derivative for the first part, I don't have it up on the screen, but you should have it on your paper, right? What do we get for the derivative?
25 plus 18x plus 3x squared.
Plus, we're differentiating. Oh, plus 3x squared. I'm sorry. I was looking at the wrong term. Sorry. Never mind. I was still stuck on the x squared term. My bad. You're right. 3x squared. And technically here, I need to check endpoints, right? So I don't know that this necessarily works at the endpoints yet, right? So I'll leave off the equal sign. That's what we need to check, correct? Okay. What about the next one? Let me make sure I do this one correctly this time.
19 plus 6x minus 3x squared.
Yeah, thanks. Good. And that was from, oops, that was a negative 1. So it was a negative 1 to 0. Next two, we got a 19 plus a 6x minus a 6x squared. See if I can actually differentiate today. And look at the right terms that I'm differentiating. Sorry about that. And then the last one, what is it? 208 minus 120x and then plus 15x squared. Like I said, I mean, it's tedious here for the check, but this part's not a difficult calculus problem, right? Do the same thing for the second derivative. We would get what? 18 plus 6x for the first one. 6 minus 6x for the second one. 6 minus 12x for the third one. Negative 120 plus 30x for the last one. And then same endpoints all the way down. And again, the good news here is everything is a polynomial. In particular, everything we start with is at most a cubic polynomial, right? It's possible when you're doing cubic splines that your cubic term is actually 0 on a piece. It just depends on what the points are that you're given. You're probably going to get a cubic piece, but it's possible that the points came from some other function that was a quadratic or a linear function, and you may be missing those other terms. But at worst, it's going to be a cubic. So at worst, your second derivative is going to involve linear functions. Let's check the natural part first. The natural part says that the second derivative at the left and the right most endpoints is 0. Right? Or technically we should say that the limit as we approach those endpoints from the appropriate sides is 0. But again, we have polynomials, and when we do limits of polynomials, we can just do direct substitution to evaluate those limits, right? If I put negative 3 into the top piece, do I get 0? Yeah. Put 4 in the bottom piece, do I get 0? Yeah. Okay. So the natural part, the natural condition is satisfied here. Okay. So since the limit is x approaches negative 3 from the left, is equal to 18 plus 6 times negative 3 is 0. And likewise, as we approach, negative 3 from the right, I think I said left when I said it. X approaches 4 for the second derivative is negative 120 plus 30 times 4, which is also 0. The natural part, I'll put that in quotes, condition is satisfied. And then the other pieces are similar. We just need to do it for the derivative pieces, right? We'll put a negative, well, since we're calculating limits of polynomials, we'll put in -1 into each polynomial. We should get the same answer. Put in 0 into each polynomial, get the same answer, right? That's what that better happen, correct? And then the same thing for the second derivatives. So we just do a couple of these. Like I said, it's tedious, but it's not hard from a calculus perspective, right? We put in -1 into this one, we get 25 minus 18 is 7 plus 3 gives me 10. I did that right. Put -1 in here, I get 19 minus 6 is 13 minus 3 is 10. So it matches there, right? And then continue down. This one's super easy, checking it at 0 because I get 19 in both of those. That one's super easy. And then the last one here, if I put in 3, numbers are going to get big. 19 plus 18 is 37 minus 54 is -17. 208 minus 360 is -152. And then plus 9 times 15 is what? 135? Did you do that right? Same thing. I better get the same thing, right? -17. I think it says -17. Yes. Okay. So it's just a matter of checking each of those pieces, right? So that's all we need to do to check that this is a natural cubic spline. I need to put in -1 into the first two pieces, put in 0 into the second two pieces, 3 into the third two pair of pieces, right? Make sure they match. Do the same thing for your second derivative now as well. We need to make sure all the curvatures match. So put a -1 here, we get 12. Put a -1 here, we also get 12. Put in 0 into each of those, we get 6. So it matches at 0. Put in 3 into both of those, we get what, -30? Yeah. Okay. So just to write down the values, we're doing we're checking that the one-sided limits exist in that case. So we really do get whatever I said that was 10 for this one. And this one was 19. This one was, what do we say, -17? I remember right. This one was 12. This is 6. And this was -30. That's all we're doing. If a problem asks you to check something is a natural cubic spline, this is what you need to check. If it doesn't satisfy those conditions, then it is not a natural cubic spline, and you should be able to explain why it's not, how it fails to be a natural cubic spline. Does that make sense? So if we look at something like, this is number 7 in the text as well. Let's do 7. I'm not going to do the whole thing. Let's do 7a. 7a gives you the function s of x equals, first part is x plus 1, -2 less than or equal to x less than or equal to -1, x cubed minus 2x plus 1, or -1 less than or equal to x less than or equal to 1, and x minus 1, or 1 less than or equal to x less than or equal to 2. This asks you to list all the ways that this particular function fails to be a cubic spline. The first one we went through and showed why it was a cubic spline. This says, look at this one and tell me why it's not a cubic spline. Yeah.
How do you verify the behavior so that like X is greater than or equal to -3 on that first one? Like how do you get to that? Because the original.
How do we get to that? They're just so it would be depending on what the data was given to you. So if the data was given to you that you started the -3 comma whatever you get when you plug in -3 into the function, that's where your leftmost endpoint would be. It depends on what the data is that you're given. All right, so the first part I would probably check is make sure the natural condition is defined. Well, if I look at the second derivative of the first piece and the last piece, what do we get? 0. So that part's okay, right? So it does not fail to be a natural cubic. I should have wrote natural cubic spline. It doesn't fail to be a natural cubic spline because for the endpoint condition, because the second derivative at the endpoint is 0. They're linear functions, right? Okay. So let's start moving into the interior positions and see if they match. Let's do the continuity and then continuity of the first derivative and then continuity of the second derivative, right? Making sure the pieces match, pieces of first derivatives match, pieces of second derivatives match, right? Looking at the interior points, correct? Okay. So let's do the derivatives. Let's do first derivative and second derivative. Well, first derivative is 1 for the first one, right? It's 3x squared minus 2 for the second one, and 1 for the second one. Right? And then we already just established that the second derivative was 0 for both of those. Here it's 6x. Yeah. Okay. So do the first derivatives match at -1? Yeah. Do the first derivatives match at +1? Yeah. Right. If I put a -1 into the second piece, that would be the limit from the right at -1, correct? And then we get 1. And then if we put look at the limit from the left at 1, it's also 1. It matches that piece, right? So the first derivative is not the problem. So just to write that down, we see that the limit as x approaches -1 from the left is 1, which is also the limit as x approaches -1 from the right. And I'll do it this way, just because it matches the direction that we're thinking of the things coming from. We see the limit from the left and the right for the first derivative at -1 and at +1 is the same, right? I know I wrote it backwards in the second one because I'm thinking about left, right for this one, and then left, right for this one. Trying to think of it that way. Anyway, it doesn't matter. I know I wrote it backwards. That part okay? So again, it's not the first derivative part. So the problem says list all the ways that it did fail, so it must fail somewhere else, right? Where does it fail in this case? Yeah, the second derivative, right? The curvature is not matching at -1 because the second derivative coming from the right-hand side is what? At -1 when we come in from the right, it's -6, right? At 1 when we come in from the left, it's 6, right? So the limit as x approaches -1 from the right, the left here is 0. The limit as x approaches -1 from the right, you just told me was -6, right? All right, so that's a fail. And also when we come in from 1 from the left, you said that was positive 6, and the limit as x approaches 1 from the right, you told me is 0. So that one doesn't work, and that one doesn't work. So in this case, this is not a cubic spline because the curvature conditions don't match. Does that make sense? All right. So that's all this particular problem is asking you to do, is just check to make sure that those things are matching or not matching. And then again, like I mentioned, if you're doing splines in practice, which people do because they're trying to approximate different points on different things by bending functions around, you might want to get even, pardon me, even smoother conditions depending on what the application is for. Right? But to make it even smoother would mean that you would not just match first and second derivatives, but maybe you would match third derivatives, fourth derivatives, so on down the line. It just depends on how smooth you want to make things. We're not going to do it any smoother than that. Okay. Then there are other little changes to splines that you can do as well, and that pops up in the if you look in the book, there's another section on what they refer to, I think, as B splines. But we're just going to concentrate on doing the cubic ones and call it good. And if you want to do further applications because of whatever you're choosing to do with your career path, you can do those further applications. We're just doing an introduction here. All right. So we mentioned that the reason why we put the natural cubic spline condition on the function was so that we could actually get enough equations to solve for all of the coefficients as a unique solution, right? When we came up with the system equations to start with, we said that we had, if I remember correctly, 3n minus 3 unknowns to start with, and then we came up with 3n minus 5 equations. We were 2 equations short to get all the unknowns that we needed. So we said, okay, we're going to impose these 2 conditions on the endpoints and help us figure out the solution that we needed, or a solution that we wanted, I should say. But that's not the only way we could do it. We said, okay, well, we're going to make the curvature 0, but we might do it other ways. So one of those other ways that we might do that is what's referred to as a clamped spline. If I can find this phrase in the text. So what we mean by a clamped cubic spline well, by clamping, we mean that we're going to set what the slope has to be at the endpoints. Okay? So for clamping, we would set if I use S again to use the spline function, we're going to talk about the first derivative at the leftmost endpoint, which your book uses a T, so that's why I'm putting a T in here, is equal to some specific value. So it calls it, in the book, it calls it a D. Well, then you can probably guess what it's doing at the right endpoint, right? If you're going to force a particular slope on the function at the left point, then you're also going to force a particular slope at the right endpoint, right? And it would depend, and that would just be a choice again that you're making, depending on what the function might look like, right? Or what your data might look like. So what I mean by that is maybe I have some point here, and then I've got another point up here. Would you want to force that slope to be positive or negative if that was your data? Positive, right? Do you think if I put the straight line through there and make a slope, or make a line that goes through there, do you think the slope that you should force at the left-hand endpoint should be bigger or less than that? So I think again that would depend on maybe where the next point is, right? What if the next point were down here? Do you think you would want to make it bigger or smaller based on the types of functions that you're dealing with here? Okay, well, smaller would go that way, right? Bigger would go that way. So you think you would make it bigger or smaller to that if everything's going to be smoothing out here? I'd probably make it bigger, right? Because I want this to go up and turn around and come back down again, wouldn't we? Versus if you had 3 points in a row, all going up, maybe like that. I probably want to go this way, and so then it can turn back around that way and make it smaller. It'd be based on what the data was, right? You wouldn't just arbitrarily pick one value and say, I'm always going to use this value for every single scenario. You would base it on whatever data was coming in and say, okay, I'm going to try to mitigate what's going on with the slope. What you would not want to do in any event, unless your points fell in a straight line, was use the slope that is that line, right? Because then all you're going to end up with is trying to make it there, and it's going to end up with a sharp corner there, right? Or at least, or it won't be necessarily sharp, but you're going to have to make it bend quickly. And that's not what you would want to do. You don't want things. The whole point of this is making things to try to smooth things out, right? I don't want to make things that bend quickly. If you think it from an application standpoint, you don't want to make, you're looking at building something, you probably don't want to make it bend fast, right? There's all sorts of reasons why you wouldn't want to make something bend too quickly. Make it weaker, make it, if it's going through water or going through air, it's going to make it turbulent, right? There's all sorts of reasons why you wouldn't want to make something bend quickly, you want to make it bend slowly. Okay. So again, you would base it on whatever the data is and adjust your initial slopes accordingly. If you were expecting your data to repeat, if you do any type of business applications or necessarily business applications or something that's going to be repeating every so often, so maybe temperature modeling, you would expect the temperatures would repeat every so often, right? Just based on how the Earth moves, right? You would expect temperatures to repeat, or if you're doing sales modeling from a business perspective, you expect sales to go up and down depending on time of year, but you expect to kind of repeat again, right? What you might want to do in those cases is what's referred to as a periodic cubic spline. If it's going to be periodic, then you would expect that everything's going to start repeating as you get from the left endpoint to the right endpoint. If it's going to be periodic, then you would expect that right endpoint to become the new left endpoint and repeat again, right? So in a periodic cubic spline, you would expect that your left and right endpoint would have the same output. The slope at the left and right endpoint would be the same. And your curvature at your right and left endpoint would be the same. Again, you would use something like a periodic cubic spline if you expected whatever data you were getting to be something that would be, at least this is in my mind. I don't do splines in practice, I'm an algebraist. But this is what I would expect why you would want to do something from a periodic cubic spline idea. You would expect that you've got this set of data going over time, and you would expect that in the next time interval it's going to repeat and have a similar pattern, right? Well, if it's going to have a similar pattern, then I should start and end with the same type of information that I had to begin with, right? And then I can just repeat that pattern again and hopefully repeat that pattern again and so on down the line. The reason why we would have different types of cubic splines, again, remember when we came up with those systems of equations, we said that we had to have more information to be able to solve the system and get a unique solution. So imposing conditions, whether it's the natural cubic spline condition and saying that the curvature at the endpoints is 0, or the clamped cubic spline saying we're going to force what the slope needs to be at the left and the right endpoints, or forcing the periodic cubic spline saying I expect this pattern to repeat again. Those are all just to give us extra conditions to be able to solve the system. That's all it's involved. It's the only reason why we're doing it. Okay? Now notice with the natural cubic spline, that allowed us to make it a little bit simpler system of equations to solve. But I want to make sure that you know that these other types of splines exist because there might be reasons why you would want to use them. Any questions on that again? Again, the thing I want to emphasize here is when we pick natural cubic splines because it made the system of equations a little bit easier to solve, and they also work in a lot of different applications. But that's not the only way we can do it. But we have to do something, right? If we're going to get a solution, one solution, we need to do something. We have to impose extra conditions to make sure that we can solve for those extra unknowns that we have. Does that make sense? Okay. All right. So let's go back. I want to go back to the spreadsheet that I sent you because I want to talk about how we had a slight error. It was just a small error, but it was enough to throw things off. And again, why did you? There it goes. It was enough to throw things off. I think I'm going to need to open my email because I didn't actually. I don't know if I saved it or not, but send it all to you on Tuesday. That's not today. There we go. Tuesday. There we are. Should have had this loaded beforehand, but I forgot. Because it's what I do. I forget. All right. So just going back, and you should all have this spreadsheet because I did email it out right after class, right? All right. So remember how we created each of these pieces? These were just the data points that I gave you. The little deltas, again, are what? The changes in the x's. The capital deltas are changes in the y's, right? So going over to this one again. Remember that that tri-diagonal system that we have, and I'm not writing on Excel again because that was a mess last time. Remember the tri-diagonal system that we have. Since we're doing the natural cubic spline, that first row is 1 and then a bunch of zeros, right? Because we're trying to find the C's. The next row starts off with little delta 1, 2 delta 1 plus 2 delta 2. Delta 2, and then the rest are zeros, right? Okay. So that 2, the 10, and the 3 is those three values, right? And we could, well, you can see that the 2 is that value, the 3 is that value, and then the 10 is the 2 times the first one plus 2 times the second one. Okay. All right, remember that the next row is actually diagonal across, right? So this is delta 2, 2 delta 2 plus 2 delta 3, and I don't know why I always want to forget the 2 in there, right? So the next one is shifted, isn't it? In the system. But when we're doing copying and pasting in Excel, shifting, the whole point of using Excel is those relative cell references, right? And it's a lot easier to just highlight and drag than it would be to copy and then move down a row and shift over one and paste and then down a row. I mean, that's not the point of using Excel, right? You want to make it easier, not harder. Okay? Especially if your system gets larger. If my system's larger, I'd like to just pull this down and be done, right? So that's why I've got it stacked this way rather than diagonal. However, we do need to make sure that we remember that things are diagonal when we do the next step. Right? All right. The next column that I have over here are your constants. Remember that was the 3 times the difference of consecutive ratios of capital delta to little delta. So if I go back into the formula here, this is capital delta 2 divided by little delta 2. This is capital delta 1 divided by little delta 1. Right? The difference of consecutive ratios of the deltas, and then multiplied by 3. This stuff was all set up correctly. Okay? It was just one little error that we made. But I'm going back through this again because I do want to start to convert this over to R. That's my goal for the rest of the class today, is to start working on the code to get this into R. Okay? All right. So when we do the elimination process, remember again that this one here is going to kill off that delta 1 and not change anything else in the row, right? So I copied it over, but that 2 there doesn't really do us anything, right? Also remember that in the very, very last one, you've got a delta n minus 1 in that final column and a 1 right below it. Again, that's the natural cubic spline part. Again, this 1 right here is going to kill off the delta n minus 1, right? And not change anything else in that row. So this 4, that's down here in the lower right-hand corner also, it's in here because I'm, again, pulling things down to copy, but I'm never going to use this 4 that's in the lower right-hand. You're never going to use whatever's in the lower right-hand corner, and you're never going to use what's in the upper left-hand corner, because those are going to get canceled off, or eliminated, I should say, since we're doing elimination, by the 1 that's in the upper left-hand corner of our original matrix and the 1 that's in the lower right-hand corner of the original matrix. Does that make sense? Okay. All right, so here was where the issue was. Remember that I want to work off, when we're trying to get rid of this delta 2, I want to work off of this number that's right here, correct? So we did that ratio, right? We did negative this over this. The problem is that, remember, I'm working down. Each new row below it depends on this one, right? And the one before it. As I work down my rows. So I'm using this 10 right here to get rid of this 3. But remember, in the computation, this 3, we also work off of this 3, multiply it by that negative 3 over 10 in this case, right? And add to this number. That's where the 15.1 comes from, right? Here's where we had the error in the spreadsheet last time. I was always going back and using the H column, right? But I don't want to use the H column for every single thing because the number changes here, doesn't it? I want to use the N column to make my multiplier, not the H. Okay. That was what the issue was. Okay. So notice this is why it was close, right? Well, 16 is pretty close to 15.1. 18 is pretty close to 16.3. That's why the numbers were close when I compared it with what I had, right? But it wasn't quite right. It wasn't quite right because it wasn't right. Okay. All right. So going in here now, whoops. I do want to, I'm trying to kill off the things that are in column G. So the G4 is correct here. But we had H3, right? Working off of this 10. When we put H here, it was always going back and grabbing these numbers as opposed to grabbing the new changed numbers. Okay? So it was just, like I said, it was a small error. It was one letter, right? Instead of working off of this number here that I have in H, I should have been working off of this number here that I have in N, which, yeah, to start off with, it is the same number, right? But remember, I want to copy it down, and it's going to change each time. And so that was what was throwing things off. Okay. So literally, it was one letter. We were grabbing it from one spot. Okay. Now, again, when I set this up for you and sent out this new email, when we were doing this in class together, I was putting everything going down because I wanted to make sure you could see it all on the same screen. That's not very convenient if you want to make a bigger set of data, right? So if we have a bigger set of data, I want to be able to take this and just copy down, right? So that was why I put everything in one line for you, so you could copy it. I believe I sent you a set of data to check, see if you could change it and make your spreadsheet bigger and see what would happen. Okay. So let me go grab that real quick. Oops, that's not where it was. It's over here. Come over here and let's see if I can do this cleverly. Oops, where'd that go? That was weird. Oh, so there's this tab in there. That's all. See if this will work or if it's going to be mad at me. Yeah, that's what I kind of figured. I'll just retype it. The 1, 2, 3, 4. We got 6 of these things, so I just need to add a row in here so I can see. I did miss one. Thank you. I was like, wait a minute. I just had to add a row in there because there was one extra point. All right. I was hoping I could just copy and paste easily, but that was gone by the wayside. All right. So the whole point of this was that I should be able to just copy this down, and that gives me my new deltas there, right? Just take that last row, pull it down one spot, because I just added one row, right? Yeah? Okay. This one, take it, pull it down one spot. Yeah? This one, same thing, take it, pull it down one spot. Right? I'm just creating the new system of equations here, right? Okay. Do the same thing over here now. This should give me my forward elimination, right? Okay. So this is the forward elimination part here where we're trying to get rid of those things down the lower diagonal, the one that's right below the main diagonal. Okay. This part okay so far? Hopefully if you're working off of my spreadsheet and you typed in the numbers correctly, you should be getting those. And if you're not typing in right now, that's perfectly fine too. Okay. All right. The little bit trickier part, remember, is that we've got to work this backward up. We have to do the back substitution, right? So remember, the formula that's here in the last one's a little bit different than the formula that's here, correct? However, this is not so bad because what I should be able to do is just take this. I should be able to pull this down one spot. That should be the correct formula now for this one because remember we take this and divide it by that, right? Because again, we're ignoring that one that's in the lower right-hand corner. That one doesn't matter. That one gets eliminated by that bottom right one. Okay. Now I should be able to get this one changed by just taking this and pulling it down one. Because this should be the right formula here now. So remember how we get this one? You take your previous answer, which is down here, right? We're plugging it into this equation. So that S6 times the O5, the S6 is our answer to this equation, ignoring the 1.04, plugging it in and multiplying it by that 1.18, right? Subtracting it to the other side, which is what we've done there, and then dividing by the N5. So you have to do a little bit of finagling on the last column because remember your bottommost one is just a ratio of two numbers. The rest are that back substitution idea. Yeah.
Can you click on
Yes. Here?
Yes.
It should just be the one that's copied down from N5. You should be able to just get that one from copying it from N5.
Okay. It's like very similar, but the decimal is a little bit off.
Shouldn't be. Let's go on. Oh, it's the same problem. You got H still in there. Yeah, so let's go back up. Go back up to N3.
Oh, it's gonna.
Yeah, because you just need to change that one to an N and then copy it down. I think that was the same, wasn't it? Oh, except your last number is not right. What's going on with this one? It's right here. Trackpad doesn't work. Oh, it's because this is not quite right. Oh, those numbers are. Why is that number so far? Yeah, those numbers are off. That's K3, G4. Oh, it's these numbers are way off. Oh, I know why. Your data, you need to change these numbers here. Those aren't the same numbers. That's why. That's what's causing the problem for you. Your last number is correct, but the other numbers aren't right. That's why your numbers are off at the end. It's these numbers are the ones that you should have right above that. And it's in the email that I sent the other day too. All right, so again, you have to finagle it a little bit for that last one because remember it has to be the ratio of 2. The rest should look the same. But the other ones now you should just be able to copy down. So these two you should just be able to copy straight down to the next line. There shouldn't be any issues with those. And now you have your coefficients. So again, everything, pardon me, everything in the spreadsheet, if you have it set up this way, should just be that you need to be able to pull it down to copy as how many data points that you have, or delete back up, depending on how many data points you have. The only thing you have to worry about is that very, very last one here is different than the rest of those, right? So the only thing you have to worry about with that back substitution step is that this is just a ratio going back up. The only thing you have to worry about. Questions on that one at all? Or at all? Yeah, Lainey.
Which box in the S column did you change initially?
So initially, this here, that ratio, that Q6 over N6, was in S5. It was Q5 over N5. This would have looked like Q5 over. It would not have had this part right here in it. Right? Okay. So all I did was I just took that cell and copied it down 1, so it was the same formula. But you could literally, whatever's in the last row, you could literally just do this divided by that Q. The last one here is in the Q column, and divide it by the last one that's in the N column, and then just copy down from the top and go all the way down to 1 less. Pardon me. Is it the only? Like I said, the only thing I have to worry about is making sure this is the right ratio. Now, honestly, since there's a 0 here, now that I think about it, since there should be a 0 here, as long as there's a 0 here, I should be able to copy this down. It shouldn't change anything. Yeah. So now I don't have to worry about it. The reason why is because as long as there's nothing here, it'll treat it as a 0. And if it treats it as a 0, then that place is going to go away and you get exactly what you need. So if you do it that way, then you shouldn't have to change anything. You just have to remember to make sure that very, very last thing is a 0. It makes sure there's nothing below it. Because it is pulling the number that's from below it, right? That's what the formula says, doesn't it, right here? It says pull the number from below. Okay. So as long as you keep it that way, then you shouldn't have to change anything and you can just pull it down. Again, moral of the story, you have to be careful in that last lowermost C value, making sure that it's not pulling something that you don't want. Everything else should just be dragging it down because it works from top to bottom. But now this should be set up for any problem that you come across that's cubic splines. You should be able to go over here to the left, replace your X values, and everything else should change. Whatever those X values happen to be. For example, if we go back to let's go back to that very first problem we did in class, where we said show that it really is a natural cubic spline. If we put in the endpoints that cubic spline goes through, it should give us the same polynomials back out again. Right? Should. Okay. So if I click back over here, there was our function, right? That we had. So notice that I'm going to need to do, I'm not doing this in my head. Sorry, doing this in my head. Let's do it. I can do it this way. So the X values were -3, -1, 0, 3, 4, right? Those are the X values that we had. The Y values would just be plugging in those into the function. So this should be 28 plus 25 times that plus 9 times a2 squared and then plus a2 cubed. Right? So you should get 7 out of that one. This one should be 26 minus 19 plus 3 plus 1. Putting a -1 into the second one. Right? The next one should just be 26. This is what I get when I put 0 into the third one. Right? The fourth one should be -163. Oops. Equals -163 plus 208 times 3 minus 60 times 9 plus 5 times 27. And then finally, the last one should be with the same function as when I plug in 4. -163 plus 208 times 4 minus 60 times 16. And then plus 5 times 64. 29. Right? Now this one, I don't need the last row that's in here because I've got one fewer data point, a set of data points here. One fewer point. So I deleted off the last row because I don't need it anymore, right? I have 5 data points. I only need 4 rows in my system that I'm solving. So I deleted it out, but everything else should be right. Say it again? It should be okay because I'm referencing the S6, which has a 0 in it. So it should be okay. All right, so notice that the coefficients don't quite match, but remember that the way we came up with the coefficients for this was what? Those coefficients are in powers of x minus the left endpoint of each interval, right? Right? Okay. So going back here to the original, notice our first y value is a 7, right? But our first x value is -3. So coming back to here, and I am going to write back on Excel on this time because glutton for punishment. Your first one should be, what did I just say it was, -7? Or is it 7? I already forgot, 7. Okay. It's 7 minus 2 times x plus 3 plus x plus 3 cubed, right? This was the first y value. This is your first b value. Your first c value is 0. And your first d value is a 1, right? We agree with that? If we multiply this out, what do you get? Oops, 27. Here I get an x cubed. Here we get what? A 9x squared, a 25x, and a 28. Which is exactly what they had for the first function, wasn't it? Yeah. And you should be able to check the other ones too. Make sure that we really do have the same thing. The last one should be pretty straightforward to check. So this, you would use powers of x minus 0, right? This is the one that corresponded to the 0. I've got a -2x cubed here. Yeah. I've got a 3x squared. I've got a 19x. And if I scroll over, I get a 26. So I really do have that one too. That one was pretty easy to check. Oops, that was farther than I wanted to go. All right. So this really does match up with what we had with those particular functions in that first problem. Again, it should go in reverse, right? The reason why we make those extra conditions is so that we get a unique solution, right? When we checked that the function they gave us was a natural spline, a natural cubic spline, so it has to be the natural cubic spline that goes through those points, right? There can't be a second one. So if I put in those points, those knots associated with that particular spline, I better get the same answer back out again. Otherwise, something is horribly wrong, and we shouldn't even be studying this stuff. Now, you may already think that, right? If something is horribly wrong, I shouldn't be studying this stuff. All right. Any of that. Again, like I said, now your spreadsheet is set up. You should be able to change the points on the left, adjust the number of rows that you need appropriately, and get all your answers. You shouldn't have to do anything else. The spreadsheet's all good to go now for any natural cubic spline you come across. If you do a clamped spline or a periodic spline, then you'd have to change some of the ways that you're solving the equation. But we're only going to deal with the natural ones, so you don't have to worry about that. However, if you wanted an extra credit opportunity, you can adjust your Excel spreadsheet, and later on when we do the R code, you can adjust your R code to work with the clamped or the periodic, or both. You want an extra credit opportunity and adjust that up. See how that would work. Especially from a programming standpoint, working with the clamp shouldn't be that difficult. Should be an easy change once we get the other code done. All right. Any questions at all about what we mean by a spline? That's important, right? what we mean by a spline, what the conditions are telling us. Spline's okay as far as that goes? Any questions about the spreadsheet? Like I said, what I sent you, and now what we've been playing around in class, should work for anything that you come up across that you have. That's okay? There. All right, so let's spend the next few minutes of class trying to figure out how we would convert this over pardon me, to coding it up and doing it that way. Okay. So again, if we're going to do this with code, we need to keep track of how we're solving the particular equations, right? And we only need to really keep track of a couple of things as we're going through, right? Because we should be able to generate lists of things as we go and do the computations appropriately. So let's think about what kind of things we would need. So remember again, we write this down. The whole point of being able to do this is we need to figure out what the C values are, correct? The way we are coming up with our splines, we're writing everything down in terms of powers of x minus whatever the left endpoint is of the subinterval that we're on, correct? One reason why we do that is because that keeps track of the constant term automatically. We don't have to do anything. We don't have to solve anything for that, right? Agreed? Okay. We wrote down the B and the D in terms of the C's, right? So the thing we have to worry about is the C's. Okay. So let's think about how we would do that, and then we can come back on Tuesday and get some code written up and then talk about how we're going to modify things going forward. Pardon me, goodness. All right. So if you're thinking about writing this up as a function, you probably want to bring in what your x values and what your y values are, right? So whatever you want to call your function, I'm going to write it down because we'll do some typing next time. But let's just write down what we're thinking about. Maybe call your function cubic spline, whatever you want. Bring in some x's. Bring in some y's. Whatever variable names you want to give it, I don't care. Doesn't matter. Okay. But probably as an input, you want a list of x's and you want a list of y's, right? Because you need to manipulate the x's and the y's, right? Agree with that? Okay. So I'm not going to write down all the syntax because we'll make sure we get the syntax entered correctly as we go. But what might you want to try to compute first? The deltas, right? Okay. So how do you think we might want to compute those deltas? What do you think we might want to do? What kind of a structure do you think we might want to use to be able to compute the deltas? A for loop, right? I want to loop through the x's, loop through the y's. Now, presumably, we've got a set of data points, right? We've got x's and we have y's. So I should be able to do one loop and do both at the same time, I would hope, right? If you've got different length lists, then it would be a problem, but hopefully your length of your list will be the same. I'm not doing, like I've mentioned before, I'm not worried as much about error checking. If we were doing an honest to goodness programming class, we would also worry about error checking things, right? I'm not going to worry about error checking. We'll assume that the person who's using your function isn't an idiot and is putting the things incorrectly. Okay? I know that's why you do error checking, right? You can't assume that somebody's not an idiot. Okay? Assume everybody who's going to use your stuff is an idiot. So you have to idiot proof it. Okay? Right? I mean, that's what you have to do for error checking, right? You're assuming that anybody who comes across your program is an idiot. Okay? So you have to idiot proof it. Right? We're not going to worry about that. I'm going to assume that you're not idiots. Okay? Sound like a plan? That's a bold assumption. Well, it might be. But, all right. So we should do this for one for loop. I can use either the length of the x's and the length of the y's in this for loop. I don't want to go all the way to the end because remember you're going to do differences of consecutive x values, right? So I want to do the second minus the first, the third minus the second. If the length of your data set is n, I only need to do n minus 1 subtractions, right? So we'll go the length of, you can use the length of the x's or the length of the y's, either or, doesn't matter. But I'm going to do one less than that. And then make sure, I think I've mentioned this before because I've had issues with this. Make sure that when you put this as your upper limit of your for loop, make sure you put it in parentheses. Because otherwise, it's going to create the list of numbers from 1 to the length and then subtract 1 from all of them. Instead of going from 1 to n minus 1, it'll go from 0 to n minus 1. It'll do 1 to n and subtract everything. 1 from everything. So be a little bit careful there. But inside this for loop, which again, I need braces for the syntax, but I'm going to be lazy and not write all the syntax in here. Maybe I say my delta here. I'm going to write them both as delta of x. We need to do what? I need to append something on there, right? What do I need to append onto that delta? Okay, yeah, so I need to do what the next x value minus the previous x value, right? So probably I'll want to do x sub s of I plus 1 minus x sub s of I, the way I have it written, right? For the first delta, I want to do 2 minus 1. For the second delta, I want to do 3 minus 2, and so on up the line. If I'm going to write it this way, I better have a delta to start with, right? So you better initialize up here a delta of x's and a delta of y's. Agreed, right? I better name something in there as a dummy, as an empty list to start with. By the way, I know we've been using the append command here. There's another way you can do the append command. If you replace the append with a C and do exactly the same thing, it does exactly the same operation. I don't know why you could do the same thing twice, but if you put a C here, it'll create a new list with that to start and that to end. It's list concatenation. Append will just put a single element on there. The C value will do it the other way. It doesn't matter. Either one works. But we also need to do one of these for the Y's, right? Bless you. So that should get your deltas created. We agree? That was a good start, right? Okay. So after that, we need to create, we're out of time. But after that, think about what else you might want to need to create. What did we do next in the spreadsheet? What did we do? Yeah, the tridiagonal system, right? So probably want to keep track, make those particular coefficients next, and then think about how we would eliminate things as we go forward. All right. So think about the ESSER assignment for Tuesday, if you will. Think about how you might start doing that stuff, right? How would you get the tridiagonal system coded in, and then start going through the thinking about how you would do the elimination process. Okay. All right. So our goal for Tuesday will be to write a cubic spline function that works. Okay, and then we'll talk about an assignment that I want you to do with that before I give you a major assignment. Okay, so major assignment will probably come on Thursday then. Sound like a plan? All right. Have a good one. Have a good Easter, everyone.